All right, right at 20 minutes after the hour. So hopefully you enjoyed our special segment from our guest speaker, Adam Chire. It was interesting to hear his perspective on AI, and that there are a lot of things it does well and some things it doesn't do as well yet. So I hope you enjoyed it. So next up, we have with us Nick Townsend, one of our senior engineers, regarding the Flink programming model. So just going to step out of the way, and don't forget you've got the chat section where you can ask your questions, and if we don't answer them immediately, we'll try to reserve a space at the end to review the questions. So don't hesitate to put them in. And Nick, take it away.
Brilliant. Thanks very much, Ray. So good morning, good afternoon, everyone. So as Ray said, I'm Nick Townsend. I'm one of the senior engineers on the IBM event processing capability of IBM Event Automation. And today I'm going to talk to you around the Flink programming model. The main reason that I'm here to talk about Flink today is because event processing is in itself powered by Apache Flink. And as we have our customers, as we have our clients starting to onboard onto our tooling, it's important to understand the underlying concepts that are behind the technology that powers event processing. So we're going to be talking about 4 main points today. So the first, introduction into stream processing, the actual use cases, etc., that are essentially the reason for Apache Flink's existence. Talk a little bit about Apache Flink itself as a runtime engine. I'll introduce some stream processing concepts, and then we'll look at how event processing, the IBM capability, is able to make your life easier when building out and testing stream processing applications and ideas compared to working directly with Apache Flink. So we'll start by talking, as I say, about stream processing in itself. And when we talk about stream processing, this is the idea of data processing, but doing it continuously. So you may have heard of batch processing, where the idea is you're just running your data analytics over batches of data, and you get a result, and then you run it again in an hour, or you run it again in a day's time. With stream processing, you are continuously ingesting data. So the application is always running. It's constantly getting new events, new pieces of data. And what this enables is for you to be able to act as soon as the data is generated. So the new pieces of information come through into your stream processing application, and you can immediately generate insights. You can generate an action based off the data. And so what this also then means is that you have unbounded data sources. So with a batch, you know when you can start reading, you know when you've finished reading, you know that you have ended that batch of data. With stream processing, you don't know when it ends. It is an unbounded data source. And so this brings challenges in when running analytics, in knowing when to stop, when is there enough data, when can I emit an answer, etc. But ultimately, the key thing that you gain from stream processing is real-time insights. You aren't waiting to run that set of applications against a batch of data. You are getting those insights in real time as the data is generated. And so common use cases that we see are things like fraud detection, the ability to be able to perhaps monitor credit card transactions and immediately notice when someone is spending in 2 different geographies, for example. Edge, sort of IoT edge data. So you've got series of maybe sensors in manufacturing. They're all generating thousands of events per second. And actually you want to be able to identify if maybe there's inefficiencies in a process or predictive maintenance, etc. Again, driven by that real-time insights. Another use case that we often see is some form of real-time marketing, being able to respond to your customer. So we often see this in things like abandoned cart next best action type approaches. The idea that you can detect when somebody's put something into their cart, but they didn't place an order, and you want to react immediately or as quickly as you can, rather than wait until, say, the next business day to send them a voucher. You could drop them an email within 5 minutes to prompt them into completing that purchase. And then finally, things like log analysis, so where you've got servers and applications sending all of their logs into streaming systems. The idea being that you want to maybe identify, again, possibly anomalies in intrusion detection, or other examples where there are streams and streams of data and you want that real-time insight. Now, what we actually often see is when we talk about streams of data is it goes hand in hand with event-driven architectures. So an event-driven architecture is this idea that applications themselves communicate via event logs rather than point to point. So I build an application that can produce messages onto an event log, an event broker, such as Apache Kafka, MQ, RabbitMQ, etc. My application now is decoupled. I can produce the messages and I don't necessarily need to understand where or when those messages will be acted upon. As a consumer, I'm decoupled from the producer. I simply subscribe to an event log via a broker, and I can get notified when there are new messages. So the idea behind event-driven architectures is that you've inherently got these streams or constantly updating logs of data, and those inherently give you hook points to start introducing some stream processing into that architecture itself. And so I mentioned the word event log. So an event log in itself is an append-only record of events. So an event happens, you produce it onto that log. It's there, it's an immutable log, the order will never change. But what this does mean is that you then can start bringing in the idea of multiple consumers. Multiple people can read from this log. They can start at any point in the log and continue to read until they reach the latest pieces of data. And it's non-destructive. So if I started from position 3, I could read all the events. Maybe my application crashes and I want to restart it. I could reset it back to position 3 and read all of the events on the log from that position. So the idea being that by having an event log that represents an immutable set of data, and it represents this system of record, this record of the events, you can then start to attach applications that can, as I say, consume and resume at any point and instantly get immediate data. And again, by consuming from the head of an event log, you get your events immediately. You will be notified or consume a new event as soon as it happens. And so this means that actually you can take an event log and think of it as a stream of data from the perspective of stream processing. So a stream processing engine, such as Apache Flink, will continuously consume new events from the head of the log. So every time there's a new event produced into the event log, it will be consumed by a stream processing engine. This means that the engine can think of that log as a stream. There is no endpoint. It is unbounded, much like we discussed earlier. And this also means that you can restart, as I said, from a known position in case of failure. So an event log that acts as the stream gives you some resiliency. Your stream processing engine can start running. If it hits an error, it can restart from where it were. And so this leads me to Apache Flink. Now, Apache Flink is a stream processing engine. There are many others out in the world, but Apache Flink has been created to offer essentially 4 main benefits. So by its design, it's designed for low latency and high throughput stream processing, with the majority happening in memory. This means that, again, to gain that high throughput, the majority of the processing is happening on the systems as it happens and in memory without the lag of being written to disk. And Apache Flink is designed to provide two main qualities of stream processing. That's stateful processing and timely processing, and I will move on to those concepts in a second. And as I mentioned earlier, the ability to use event logs as streams means that the runtime of Apache Flink can offer resilient processing. It can restart and continue from known positions in case of failure, or in case of replay, in case of testing. If you're building a stream processing application, you might want to just tweak it and try again and continuously send the same pieces of data, but test out the hypothesis, or just test that you're getting the expected results. And so the event log being able to be reconsumed from known positions means that Apache Flink can be used for those replay type concepts as well. So I mentioned stateful and timely, and I'd just like to drill into those a little bit further. So we'll start with stateful processing. Now, in a very basic flow, or a very basic stream processing application, you can think of it like an ETL, extract, transform, load type operation. If you're just processing every single event in isolation, you can get answers. You could maybe filter out messages you're not interested in, but it limits the use cases. You're stuck at a single message scope. So stateful processing is the idea that actually you want to perhaps take account of more than one event to be able to build an answer. So an example use case, maybe you've got a stream of click interactions on a website, and you want to understand how many times a particular page is visited. So this question is unbounded. You're saying, I just want a running count of every time a page is visited. I want to know what the total count is. And so this is the idea that there is state involved. There is state that represents the count for each of the individual pages. Every time there's a new event that changes the answer, then you get a new event output from the processing stream processing engine that will say, oh, the answer's changed. This is the new event. This is the new event. But what this means is that you've got that state held for the lifetime of the application, so that every time a new event comes in, where the engine is able to increase the count or whatever aggregation you may be using, and submit and emit a new event. So if we look at a worked example, we have at the top the red circles representing events. The right-hand side is the oldest event, and obviously new messages, new events are put at the left-hand side. So we traverse from right to left, and each time we move, we're getting a new event. So if we started and consumed the first event in the log, we've attached to the event log, and the first event we're given is for page ID 1. We know that we've only seen, as an engine, we've only seen one page ID 1, and we know the count is 1. If we skip forward through, so we now read 2, 1, 1, then actually the answers start to change. So we can say that at this point in time, we know that there are 3 events that represented clicks for page 1, and we know there's 1 event that represents page 2. So the previous number for page ID 1 was 1, where it's now emitted 3. We have an event saying that there has been 1 view on page 2. And then if we skipped all the way towards the end, then we end up with, again, new answers. We know that at this point in the event log in the stream, we can say that there's been 4 counts for page 1, 2 for page 2, and 1 for page 3. So this is an idea of bringing in state to allow you to do aggregations on the data, analysis that involves being able to answer questions around multiple events and then grouping them together. So in the analysis case, these are things like being able to detect, if we take the sensor case, maybe you're trying to spot a machine that is showing high rates of high temperatures, for example. You're counting how many times the temperature was greater than 180 Fahrenheit, for example, and that allows you to understand which of these machines are showing greater counts. Perhaps you would be looking at trying to figure out which customers are spending the most. And actually, you're only ever interested in the 10 most valuable customers, but actually you're interested when that changes. So when a customer jumps into the top 10, maybe you want to take to understand that. And this is all around keeping that state and getting an answer every time the application can provide you with a change or a new answer from that. The challenge, however, with just purely stateful processing is you're holding state for the whole time. So whilst the application is running, then you're constantly building up more and more state. Now, in some use cases, that might be perfectly acceptable. In the case where you're counting, then that count is a small piece of memory. It's not necessarily anything particularly to worry about. But if you were doing aggregation, perhaps that involved more complex qualities of the event, maybe you had a structured event coming through with customer information, etc. As the data that you're processing in a stateful manner increases in size, as does the state. And so stateful processing in itself can answer some very basic questions, but it does come with concerns and risks over data size, at which point perhaps then an approach that you might then move to is the idea of timely processing on top of a stateful model. So timely processing is the idea of being able to bring time into the calculations. So for example, you might say, how many pages are visited per hour? You're bucketing or windowing the data so that you can actually make a calculation that is a finite answer. It doesn't change. At the end of each window, at the end of each hour, you can say, in the last hour, there were this many. And that's never going to change because now you're moving on to the next hourly window. This means that the state can be discarded once the window or the hour period has been passed by. But it also means that actually once you bring in timeliness, you can start to look at more temporal relationships. So maybe you're interested in things like being able to detect has there been an order that was followed by a cancellation? So you can start to actually develop more interesting questions once time becomes part or a first-class citizen in the programming model. So when Apache Flink talks about time, it really is saying, when did the event happen? Now, when you look at things like event brokers, so such as Apache Kafka, you produce a message onto an event log. So when you produce that message, you could put a piece of information as part of that payload that represents the time of the event. That we often would consider creation time or message payload time. However, that doesn't necessarily equate with the time that it was received by the event log. So another option is the log append time. So when did the message actually go into the log itself? And then finally, if you are more interested in actually trying to understand when you processed it rather than the time the message or event was created, then Flink introduces the idea of processing time as well. That is the time when the event was being processed by Flink. So where I talked about previously the ability to replay data, if you were running with processing time and you replayed the data off an event log, then the time between two runs would be different because you were processing them at different times. If you were using log append time, every time you ran the application, then the time would be the same. It's always the time that the message, an event was added into the event log. And in the same respect with creation time, if you ran the same flow, same application multiple times, then it would be using the message time in the event payload itself, and that would be your creation time. So most of the cases that you see in use of timely processing tend to go towards creation time or sometimes log append time. The idea being that you want a reproducible event time that represents when it happened. But that's not to say that there aren't use cases where actually you are interested in just when did you process it in Flink. But as I say, for the majority of the use cases, it's the time the event itself happened rather than the time Flink was processing it. So where we talk about time, that then brings us into the idea of, well, how can or how does Flink use time as part of the processing of timely data? So we talked earlier about the idea of answering per hour, for example. So I'm just going to work us through a worked example on how events would actually end up being emitted by Flink, and how Flink knows that it's safe to say, yep, I have an answer for this hour-long period. So if we start with the set of events at the top, imagine we've consumed 3 messages from this event log. We've got one at 1 o'clock, another one at 1:10, and another at 1:50. If I were bucketing these into hour-long windows, then my hour starts at 1 o'clock and it ends at 1:59 and 59 seconds. So we can see here that there are 3 events that have gone into this window. But at this point in time, because it's an unbounded data stream, Flink doesn't know if there's going to be any new messages coming. It also doesn't know if the next event that comes off the event log will be at 1:51 or at 2:30 or at 2:54. So this window, this bucket, remains open for more entries to be put in as they're consumed from the event log. And so this is where Flink brings into the concept of open and closed windows. And right now, Flink is unable to close the window because it doesn't know if event time has progressed far enough to say this window, that's it, there will be no more events. Now, the reason Flink is interested in this is because it expects events to ideally be in order. So in a perfect world, every new event on the event log would have a newer event time, and Flink would just know that the next message it reads will have a newer timestamp. But even still, we're in a position where Flink doesn't know or is unable to say, I can close the window between 1 and 1:59 because it doesn't know what the next event will be. However, the moment that we then read the next on the log, it's at 2:30. So Flink is able to confidently now say that there will not be another event earlier than 2:30. There certainly will not be another event in the 1 to 1:59 space. So at this point, the 1 to 1:59 window can safely close, and Flink can emit an event. So let's say I was trying to just count how many things were in the window, then we would be able to say that the 1 to 1:59 has 3 events in it. And we then still can't answer for the 2 to 2:59 because we don't know if it's safe to close yet. So if we skipped all the way to the end, then we can see that each of the individual events get put into particular windowed buckets. And the yellow ones represent, this is where Flink has been able to say, I've seen event time progress enough that I can close the window. And the green is still an open window where it's waiting for new events to be able to increase the understanding of where the event time currently is. So Flink does this via a mechanism that it calls the watermark. So as each message is being read from the event log, Flink will periodically be asked to, or has a timer that says, please insert a watermark into the stream that is being processed by the runtime. And a watermark says this, at the point I'm asked to generate a watermark, Flink will be saying, this is the most recent time that I have seen whilst processing any events. And so the watermark in itself is essentially a guarantee that says any further event is going to have a newer time than this watermark. And so that means that once the watermark has been emitted by Flink, that is a way of being able to say, I can close the window. So where we saw that 2:30 event being consumed, and then Flink closed the the window. That was because the 1 to 159 window. That was because a watermark was able to be generated by Flink that said, I've seen 230, and therefore the guarantee that there will be no earlier events than 230 allowed Flink to use that watermark to close the window. Now, in a perfect world, every single message would actually be sent and added to the event log with an event time that is newer than all events that currently are on the log. However, there are many occasions where this actually wouldn't happen. For example, if your event producer in your application or in your event-driven architecture, if a producer is, say, using mobile data and it goes through a tunnel and it's about to send a message, but it can't because it has no internet connection, then maybe it will store the message until it gains the reception. And once it has reception, it will then submit that new event. Now, if in the meantime, other producers that had internet access were able to produce their messages, then this queued event will arrive onto the event log with an event time that is earlier than other than messages that are already on the log. And so this is where in the real world you can actually end up with disordered streams where events arrive later than the watermark itself. And so as part of understanding the Flink programming model, we really do have to be mindful of the disorderedness that can exist in the real world streams of data. So in this worked example, it's very similar in terms of we've got the same set of events that we just walked through from the window perspective, but the difference is that the times that the events represent are not in order on the actual log that is being consumed by Flink. We can see that there are messages at 2:30 that happen on the event log before we then see, for example, a 110 appearing. So what this means is that if we start to walk through again as normal, we read our message at 1 o'clock, we read the message at 1:50. Both of those happily go into the bucket, the open bucket for 1 to 159. We then get 2:30 coming off the event log, and 2:30 now means that Flink is able to close the 1 to the 159 bucket. However, we now read the message at 1:10. This message is late in terms of it has arrived where it has an event time that is earlier than a message that's already on the log. Flink would look to put this into the bucket for 1 to 159, except it can't. It's already closed that because of the watermark generated by the event at 2:30. So this event is not only late, in the case of a timely operation in Flink, this message is now discarded. It doesn't contribute to the answer of how many events are in the window. The answer was emitted as 2 events once the watermark closed the bucket, and this new event is too late. It does not contribute to the answer. In the same way, we then carry on forwards. We read an event at 3:15. That 3:15 event has closed the window between 2 and 2:59. And if we skip to the end, we can see that the 2:35 event did not make it into the bucket. It again is considered late. And so where we have disorder in the streams and events arrive late, when you're writing applications that involve timely processing, late events that legitimately have been produced will end up or can end up being discarded from the events that you will then be emitting as part of that flow. Now, Flink introduces the idea of lateness as a concept, and what that really means is a mechanism by which you as an application developer, when you're writing your stream processing application, can account for these kinds of real world fluctuations in delivery, in disorder on the stream. So if we again take the example of a window from 1 o'clock to 1:59, if the watermark that is generated based off the most recent event time, then at 2:30, Flink was told to emit a watermark, and it emitted the watermark of 2:30, and that closed the window at 1:59, between 1 and 1:59. If you want to account for lateness, however, you can configure your sources of data, the consumers from the event log. You can configure them to say, well, actually, when you're asked to generate a watermark, let's delay it slightly. So the idea being that actually, rather than just using event time, take event time, but move it an hour in the past. So if the event, for example, came in and it said 2:30, then the watermark would be 1:30. If the event was 3 o'clock, then the watermark would be 2 o'clock. Now, what this means is that you are able to allow for that late data to arrive because you're delaying the watermark, and it's the watermark that causes Flink to say this window can safely be closed. And the reason this is important is that it does have to be part of your internal modeling when you're building and thinking about the programming model that stream processing requests, that Flink expects you to use. Lateness is intrinsically important in understanding how and the shape of your data, the quality of how late you expect data to be, and whether or not you care about it or not as well. Because of course, if you're running some processing that actually you're going to get millions of messages, and it's not that important if one of them didn't get included in the processing, then actually knowing you've got late data is important, and you can actively choose to not account for it. However, if you actually do explicitly want to care for the late data, then that's where we would use the watermark and change the calculation to ensure that you are protecting your data from this quality. So if we think about lateness now in the previous example, if I set the watermark calculation to actually be the event time minus an hour, then we see that all of the events now end up in their appropriate windows before the window has been closed. So the event that arrived late at 1:10 was late because previously the watermark was 2:30. However, if we delayed the watermark by an hour, the watermark would be 1:30. The event arrives at, we consume the event and we see it has an event time of 1:10. We can safely put that into the 1 to 1:59 bucket because it hasn't been closed yet. The watermark is still 1:30. It's not closed the bucket. This means that the late events are now included in the window. However, the implications of this, and again, the reason this is important from the overall programming model, is that the events are contained inside the buckets, but you'll notice that two windows are open now, the 3 till 3:59 and the 4 till 4:59. And the reason for this is because the event at 4:30 has a watermark of 3:30. That means the 3:59 bucket cannot be closed. We need a new event to come through that has a event time of 5 o'clock to be able to give a watermark of 4 o'clock, which allows us to close the 3 to 3:59 bucket. So the implication of this, and the reason this is important, is because if you've got data flowing in real time, if your data is constantly increasing based off a clock tick, then in order to account for events that may arrive late, your answer for the 3:59 window does not occur until 5 o'clock of real time, at the real clock time. And so when you are building your stream processing applications and you're using lateness to protect against late events, it means you are also delaying the emittance or the ability to emit the answer for each of those windows. So if you're looking for a timely, if you're looking for say a prompt answer, you want to know as soon as the window closes, then you have to accept that late data will be discarded. If you're happy to delay the answer to account for lateness, then you can get more of a correct answer, but you had to wait for however long you've delayed the watermark for more events to progress forwards. Again, I'm laboring the point here because these concepts help to explain behaviors that you may see whilst building applications in Apache Flink or in IBM event processing as well. The idea being that you account for lateness, but you don't necessarily see the answer based off the data that you're testing with. And so you just take account of lateness and the watermark and the implications as part of designing and configuring your applications. So now we've talked about timely and stateful processing. I just want to talk a little bit now around some other concepts that you see appearing in Flink. They're common to other stream processing engines, but they're also very common things within Apache Flink as well. And so the four common, I say, operations, the idea being you build an application, a stream processing application from a series of connected operations. But for example, things like aggregation. So that's where you try to do a calculation over a group of events. What's the total number per hour? What was the most, the largest number per hour? What was the most frequent thing per hour, etc. But the idea being that as an aggregation, you're grouping your data and then running some form of aggregation over that group. You have the idea of some form of enrichment. So maybe actually you've got very small events flowing through your event log, where those events have unique identifiers or something that represents information on another system. So as the events flow through the processing engine, you actually want to put in external data to allow you to take additional processing or generate new insights without the actual information being polluting the events that flow through the system themselves. Another common thing is the idea of joining data. So although we've talked about the examples with a single event log, in the case of joins, actually maybe you've got different event logs being consumed as streams inside your engine. So maybe you've got a stream of orders and a stream of cancellations, and you're interested in joining. So the idea of saying, I want to know, were there any orders that were cancelled within an hour of the order being placed? In that case, I would be building a join of two streams to generate new pieces of information. And then a subset to an extent of aggregation is the idea of a top N. So you might simply just say, I've got my stream of data, I want to sort it by time. So I'm going to find the most recent transaction per customer. Maybe I would sort by the value, and I'm going to find who are my top 10 most valuable customers in an hour, or just in general, making the decision between stateful and timely. But the idea being that all of these are operations that you can apply at scale to this constant stream of data, and each time you're generating new insights in real time with calculations that update as soon as the data, as soon as new events are produced as well. The other thing to talk about with Flink in itself is that Flink has three main models in terms of APIs. They have the data stream API, and the data stream API is very much around the idea of dealing with your streams as streams of data. You build them with a very fluent API where you're just essentially building chained operations. The data stream API gives you access to very low-level concepts in Flink, which means you get to control how time is processed, how the state is managed, etc. But it is a very low-level and complex API. The next one that Flink gives you, building on top of DataStream, is the idea of the table API. And this is where actually, rather than thinking of a stream as just a constant amount of data, the table API is a much more declarative domain language. But the idea is that actually each of your sources of events, and every time you run a calculation on events, you're generating new tables of data. Think of like an Excel spreadsheet or a database table that's constantly growing. But the idea is that the table API lets you reason about it in ways that are more familiar with data processing, with batch processing. And so you actually can then start to run things like some level of select commands or filtering, etc., and using a much more declarative language. And then the final abstraction on top of that is a SQL layer. So at this point, you're not even really writing applications per se. You're writing SQL code that represents a series of selects and inserts and temporary views, but a top level abstraction on top of the table API that allows you to actually just run queries rather than building applications. And so as you start to dive into and build Flink applications, each of those three APIs will obviously then fit depending on your skills and use cases. But the very nice thing about that is that it gives different levels of access for particular personas, with SQL being very much focused towards those familiar with data processing, DataStream perhaps those who are much more low-level Java programmers, for example. But having talked about the three different layers of APIs in Flink, I'd now just like to talk about IBM event processing itself. So event processing is a capability of IBM Event Automation. As mentioned earlier, it uses Apache Flink as the runtime, but it's all about primarily giving a low-code authoring environment. So a visual environment where you can iteratively build and test concepts. It follows that similar table-based programming model. So data is represented in terms of defining tables. Those tables are constantly receiving streams of data, but the operations are displayed and rendered in a tabular format. And the idea being that this helps you to visualize and build and test out ideas in a, as I say, low code environment. And as part of my demos, I will show some comparisons to help explain the point. But ultimately, this makes the capabilities that exist in Apache Flink significantly more accessible to other members of the business. You don't have to be a coder. You don't need to be building code applications. You simply are using the low-code authoring environment to author a flow that represents the transformations and the insights that you're trying to gain. So I'll start now by moving over to our first brief demo, and I will log back in. So the first demo I'd like to walk through is the idea of clickstream analysis. So the idea being I've got a stream of events coming through that represent the clicks on a website, and I'd like to do some level of analysis on there. Now, I mentioned that I'm going to try to labour the point. I don't expect everybody to read this. What I'm representing here, however, is the SQL that would represent the clickstream program I'm going to build. If you were to write this in your, if you were going to try to write this in your own environment, if you were writing Flink SQL, these are the kinds of things you would end up having to write. The idea being, as I mentioned, it's tabular based. You're creating a table, you're dealing with the watermarks, you're setting up all of your connections, etc., to a particular event source, and then you're doing some level of aggregation, etc. But it's very SQL. Well, it's SQL in itself. You have to understand the SQL to be able to write it. That sets a barrier to entry for business users who have to understand SQL in its entirety, as well as learning some of the Flink specific SQL functions that Flink has added. So as I mentioned, however, the idea behind this is just to do a windowed aggregate, the idea of please tell me how many times a page was visited. So if we switch to event processing instead, and in the interests of time, I'm going to just talk through what we've built. But the idea being that I start with an event source. As I mentioned earlier, Apache Kafka is an event broker, and in event processing, where we have event streams, our Apache Kafka capability, then we have event processing working directly with connecting to Kafka topics as their source of the event log data. So I start by going through and just connecting off to a Kafka broker, finding a topic that represents the event log I'd like to consume as a stream, and then we do some niceties. We look at the topic itself. We try to grab a sample of the payload, and that allows you to be able to just verify, oh yes, I've connected to the right topic. But the most important thing here is that you can see that there's a sample piece of data. And then when we step through, we then map that into that tabular idea. But what we do for you is we're helping you connect to a topic, find the information, and then represent that information and allow you to change the types, pick where your time is coming from for the event. So in this case, I have a field called TS that contains my timestamp, and I'm marking it as a source of event time, and I'm setting 0 lateness. So all of this was represented under the covers by a create table statement, but I haven't had to write any SQL myself. If we look at the preview SQL, we can see that actually this is what's being generated for this particular node. I'd have had to know all of these individual properties to configure the Kafka connection. I'd have had to know all of the connection details, etc. But this wizard, this low-code authoring, each of the individual nodes talks you through and helps you to understand what you're trying to build. So having created a source node, bringing the data in, what I can do now is I can actually run and just double check that I've mapped everything accordingly. Is this what I expect? So this now is live information coming straight off that topic, and I can see I've got my page, I've got my user, and I've got my timestamp. So having confirmed that I've got the right source of data coming through, my aim for this flow was to do an aggregate. I want to actually count how many times a page is viewed per hour. So I open the aggregate node. So I should have said on the left-hand side is our palette of different operations. And in this case, I'm using the aggregate window operation. So in the aggregate, I start by defining that window. I'm saying I want all of my windows to be an hour long. I'm interested in something per hour. And then I pick my functions. So I can say, well, actually, I'm interested in counting how many times the page has been visited. And because I'm interested in per page, then I add a group by to say, actually, I'm interested not only in the count per hour, but per page as well. And again, if we were to preview the SQL, you can see that in order to write this in SQL, I've had to have known how to build a temporary view, select the right fields. I'd have had to know how to build my windowing. I'd have to understand what the syntax is for actually windowing the data, and then the group by as well. Whereas within the UI, it's very much a wizard-driven experience that helps guide you to build the appropriate capability. And then we get our output properties where I can just control what pieces are being sent out from the node. And if I run the flow this time, we now are going to see the results coming from the aggregate itself. So rather than seeing the raw stream of events, we can now see that actually, for example, I know that the checkout page between 9 and 10 was visited 10 times. With the basket page between 10 and 9, I know it's visited 11 times. And so this allows me to view and very quickly be able to identify those kinds of insights. Now, the reason that I've built this particular flow is not a complex flow, but the idea that this actually demonstrates is the fact that the tooling in event processing allows you to build this in a low-code manner. It allows you to detach yourself from the SQL as a business user. I'm more interested in just using the wizard to build and control these operations. And this becomes a little bit more obvious if I switch to a slightly harder example. So the next one I'd like to talk about is the idea of maybe some suspicious behavior. So the contrived use case I have is that there's a company running a loyalty scheme. So you're a member, you have a loyalty card. And you can use that loyalty scheme to access airport lounges. You could use it to hire cars from a hire branch. And actually, what we're then interested in this particular case is, are there people who are using their loyalty card in an airport lounge, but very soon after or just before, they've also used it to hire a car? And the idea being that, well, if they're in the airport in the lounge, then they really don't need to be hiring a car. So the question would be, is this a case of something suspicious that maybe they've shared their loyalty card to help somebody else get a benefit? Now, that talked about two separate ideas, hire car and lounge. So two separate streams of data, which is leading to the idea of doing some form of join. Now, if I were to try to write this in pure SQL, then again, we start by having to create a particular table that represents the source. I then have to create a second table that represents the second source. I then have to know how to do an interval join, so the correct syntax to actually do a join that finds data between two time periods. And if we then switch over to event processing, we'll talk through again building that same flow in a low-code manner. So I won't go through the source configuration. It's the same we've just seen, two separate Kafka topics. But the interesting thing here is then the interval join. So this is the idea of being able to say, I'm looking for data that happens or events on one stream that happen within a particular time of another. So the first thing, being a join, being a match, there's a level of, I need to know how can I identify the events between the two sources, between the two streams. But I'm interested in events on one stream that have the same loyalty card as an event on the other stream. So my join condition, my match condition is that the loyalty on source 1 represents the loyalty on source 2. And then we look at our idea of a time window. So I'm saying I'm looking at my first source, my hire car, for example, and I'm interested in finding people who have used the loyalty card either within 5 minutes before accessing the lounge, or they've used it to hire a car within 5 minutes after accessing the lounge. And so the UI is helping you to understand the implications of what you're building. We can see that we're interested in finding source 2 within 5 and 5 minutes of source 1. We're interested in that 10-minute window, and it's dynamic. So if I started to tweak it, I can start to see the implications of the window, the time interval that I'm building. If we go back to 5. And then again in the output properties, this time where I've actually joined two streams together, I can get information from both of the individual events that match. So maybe I'm interested in finding both the loyalty number, but also when did they hire it, what was the transaction, when did they enter the lounge, what was the transaction, etc. And having configured that, we'll now run and just talk through the results. So again, in this case, what this has allowed me to identify is, for example, this top row, given loyalty number, we can see that at 6:32 and 16 seconds, they hired a car. But at 6:34 and 16 seconds, they also entered a lounge. So I've been able to identify this as a potential suspicious piece of behavior. I can generate this match as an event that would actually allow me to then take some action, maybe flag it up at a later point. What I haven't shown in the demo, but I will talk through now, is that obviously what we're seeing are two sources and an interval join, and the results appearing on the low-code authoring UI. This is as part of that iterative development and testing it. If I wanted to build additional processes or business applications that could respond to those insights, then what I would be doing is to drag on an event destination. The destination within event processing is a Kafka topic. So much like we have been reading our streams of data from an event log, we can write to a new topic, a new event log for other downstream applications in an event-driven architecture to be able to read as well. So typically you might imagine having now connected it up and start writing to a Kafka cluster, then to a Kafka topic, then you would perhaps have other applications that are consuming from that output that can then take action. They can review, they can trigger a process that might ask a customer service agent to review this, or perhaps if the customer is in the lounge, at this point you could then trigger a reminder or an ask for the staff to actually go and approach that customer who is obviously still in that lounge. And the value here is that it's happened again in real time. So we set that 5-minute window. So that means that within 5 minutes of the event, of the customer using the loyalty card in the lounge and it being matched with them having used it for a car, then you're taking that action in real time rather than waiting for some later batch analysis, maybe at the end of day where you try to compare all of the transactions. So ultimately, what I'm identifying or hoping to identify here is that the ability to react in real time is a key benefit of using stream processing, and the ability to build and test these ideas in a low-code environment is one of the main benefits that we gain from using IBM event processing rather than using Apache Flink directly. And in particular, where it's low code, we've seen how it allows you to abstract away the underlying concepts or the underlying code to an extent, the SQL that was generated or an underlying table API program, etc., and instead focus on looking at what you're trying to achieve without necessarily needing to understand the syntax of the programming language itself. And finally, obviously, in terms of a recap, what we've talked about today is some ideas around just stream processing, how it fits into event-driven architectures, the idea of unbounded streams of data being processed in real time. We've talked about how Apache Flink introduces concepts around stateful and timely processing, brings time as a first-class citizen, which you then have to account and understand as part of your internal mental model around using Apache Flink. And then we've looked at event processing and how it makes the ability to analyze and perform processing on streams of data more accessible to business users, those who are not comfortable or experienced in using programming languages in themselves. So with that, I will stop sharing and see if there are any other questions.
So I don't believe there's any questions I can see. Do you see something I don't?
No, certainly no question.
Okay. All right. Well, I have a question for you, Nick. You know the difference between a good speaker and a great speaker?
I'd love to find out the answer.
A great speaker ends on time. Congratulations.
Thank you very much.
Absolutely. Now, thanks everybody for joining. Don't forget about office hours. Will be coming up after the next session. Next session is on observing IBM MQ with, I believe it's Martin Evans, but I wouldn't stake my reputation on that. But we'll be over on that channel in just about 5 minutes at 25 minutes after the hour. So again, Nick, congrats, good job, and we'll catch you in 5.